Special linear transformations. This part is from 1.8 and 1.9. And in the last part, we can interpret any linear transformation into an appropriate matrix. So here we're going to introduce some special linear transformations, which means we're going to introduce some special matrix and try to interpret its linear transformation, associated linear transformation. So the first category of special matrix is called diagonal matrix, which means it's a matrix, squared matrix, n by n squared matrix, whose diagonal entries probably given by non-zero numbers. Otherwise, in the off-diagonal elements are just zeros. So for example, a general form of n by n diagonal matrix can be written as d1, d2, and dn, and 0, 0. And what it means, and the notation is diagonal, or diag, and d1, d2, dn. So this is diagonal matrix. And if you are given a diagonal matrix with all diagonal entries 1 and off diagonal 0, then this is diagonal matrix, and it has special names, so-called identity matrix. So if everything d1, d2, dn's are given by 1, then this is diagonal. This diagonal matrix is called identity matrix. And the ith column of identity matrix is denoted by EI. This has been introduced before. So EI is special vector. For example, if you have diagonal matrix, 3 by 3 diagonal matrix, then we can write this as I. For example, this is I3. I3 means 3 by 3 diagonal matrix. And the second column is called E2. The first column is called E1. This is E3. So sometimes in our homework, if we have E2 times 5 plus E1, then what you do is you want to write appropriate E2 and E1 and perform all the calculations. Elementary matrix. Second category is elementary matrix, which are obtained from identity matrix after applying an ERO. So there are 3 EROs we have introduced. One is called replacement. So ith row times k plus jth row replace jth row. This is one ERO, so-called replacement. And dik, which is multiplied by k to the ith row and switch it into Ri. And permutation matrix, swapping 2 rows I and j. So, for example, what we can, if you have, so one question, what is E? We're talking about 3 by 3 matrix again. So what is E23? 5. Then what you do is you are starting from 1, 1, 1, 0, 0, 0, 0, 0, 0, which is identity matrix, and try to do this transformation or ERO. So Ri, here I stands for the first index, so 2. So I is to R2. So R2 times K here is, our case is 5, plus Rj, J is second index, in other words, in our case 3, so R3, and replace R3. So the first 2 rows will stay the same, but the third row will be changed. So R2 plus 5, plus R3, replace R3. So this is E235. All right, you can try to figure out the next question. What is D23? What is E13? So E13, maybe I can write down E13. So suppose 1, 1, 1, you start from here, identity matrix, and then the ERO you want to do is R1, R3 swap. Then you get some matrix. This one is called E13. Okay. Now we're going to give you one interesting fact. This explains why elementary matrix is important. So left multiplication by an elementary matrix represents corresponding EROs. What does it mean? So before, when we introduce EROs, we do some manipulation of matrix by doing row operations. But we didn't know what happens in terms of matrix computation. That's not matrix computation. Matrix computation is addition, multiplication, or transpose kind of thing. So every EROs we have introduced at the beginning of the term can be formally written into multiplication or matrix algebra. So this is what it means. So we have examples. So suppose you have A, then I want to change this into RREF. The first step from here, because I saw that the first column is 0, 1, 0. This is 0. So I want to have the first item is non-zero. So what I want to do is we want to swap these two, R1 and R2. So after we do exchange of two rows, then we get 0, 0, 0, 0 in the third row, and 1, 0, 1, 3, and 0, 1, 1, 2. But this is not matrix multiplication. Actually, what we did is matrix multiplication. So what we did is E12, elementary matrix. So E12 means so E12 means swap RIIJ, swap R1, R2. E12 times A is actually B, gives B. So this is matrix multiplication. So every ERO stands for matrix multiplication by elementary matrix. All right, now we're going to look at some other special linear transformation in terms of special matrix. So we have, if you have old picture, you want to reflect through horizontal axis, x1 axis, then what you actually did is multiplying by 2 by 2 matrix given by 1, negative 1, 0, 0. And similarly, you can do reflection with respect to vertical axis and reflection with respect to x1 equals x2, this line. So there are some other contraction and expansion which are given by left multiplication of some standard matrix, special matrix, and there are some other. So horizontal shear and vertical shear. And rotation matrix, you can also, if you have some picture, you can also rotate the picture to get a new image. This rotation is actually linear transformation, and we can have rotation matrix. It depends on how much you want to rotate. So if the rotation is phi, then the matrix is rotation matrix is given by this form with related to phi. All right, with this in mind, so this is pretty much everything for this slides, but I want to do one homework problem using what we learned here. So we're going to map the matrix to transformation, given transformations. Reflection in the line y equals x. So y equals x is something like this. Then you want to reflect with this line. So this is what it means. And this matrix is what you need to multiply. So the linear transformation corresponds to 0, 1, 1, 0. So here, the last one is 0, 1, 1, 0. Dilation by a factor of 2. Dilation has not been mentioned here, but what you can think of is dilation is enlarging every direction into by multiplying by 2. So for example, if you have xy coordinate system, you want to look at 2 points. One point is 1, 0 standard matrix vector, and the other one is 0, 1. So 1, 0 is here. Then by dilation, it will so this vector, this arrow will be twice bigger. So it comes up to another point. So 0, 2, 2, 0, 2, 0. So this coming to 2, 0. And what is 0, 1? So 0, 1. 0, 1, so maybe we can use this. So 0, 1 is the point here, and if you enlarge it, so you can get this point. This point is 0, 1 becomes 0, 2. So this is 0, 2. Now what is the matrix corresponding to this dilation? The matrix is given by these two columns. So these two columns. So we can see that dilation is the same as this matrix. Reflection in y-axis. So reflection in y-axis means reflection in this axis, vertical axis. So here vertical, no, it's vertical contraction. Reflection through x2 axis, vertical axis. So we have -1, 1 as diagonal entries. -1, 1 as diagonal entries. So we can get this. Reflection in the x-axis, so we can also find from our table, then this supposed to be number 4. And identity transformation. In other words, after transformation, there's no change in the picture. Then this means you need to multiply by identity matrix. The last one, reflection in the origin. Of course, the only matrix left here is here, so you have to have this. But you need to know why reflection in the origin is -1, 0, and 0, 1, 0, -1. There are many ways you can interpret this, but one way is, so if you have some coordinate system, any point in the picture, any pixel, you're going to reflect it to the origin. So what it means is this is the same thing as you have rotation 180 degrees, which is pi. So we know that the rotation matrix here, we have given rotation matrix, but all those phis are pi. So this is cosine pi, negative sine pi, sine pi. And then we can directly get this is negative 1, 0, 0. All right, we're going to stop here.